Okay, so this is section 6-5, and now we're going to start looking at complex numbers in polar form. And we're going to end up looking at what's called Wahb's theorem. Now, you've worked with complex numbers before. We did this in Algebra 2, you did this earlier this year, and we remember that I is equal to the square root of -1. And complex numbers in general are of the form a plus bi, where a is the real part and b is the imaginary part. And we can also plot these points. Again, this is stuff we've done earlier this year, so I'll go ahead and plot some points if we move our plane down here. Remember that this is the real axis, and this is the imaginary axis up here. Okay. So let's go ahead and plot some points. If I have the complex number z equals -1 plus 6i, it's almost like plotting the point -1, 6. So -1, and I didn't give myself enough space here, 4, 5, 6. So that would be that point right there. If I do -i, there's no real part. The imaginary part's -1, so that would be kind of like this. And then there's no imaginary part for this one, there's only a real part, and so that would be like this point right here. Okay, so we can plot those points. Now, finding the absolute value of a complex number is not something that we've seen before. And the way we find the absolute value is taking the square root of the real part squared and the imaginary part squared. Now this is where students make mistakes, is they include the I in here. You just want the coefficient, you don't want the actual I value. So finding the square root of these, -3 squared plus 5 squared. Notice I did not write 5i, it's just the coefficient. And 3 squared is 9, and 5 squared is 25. So we have the square root of 34 is the absolute value of z. Okay. Let's look at our next example. We have z equals -2i. So square root of 0 squared plus -2 squared. Well, that's just going to be the square root of 4, which is 2. Okay. Let's move on to the next page. Now, let's talk about converting these complex numbers into polar form. Now, we've worked with numbers in polar form, we've worked with polar coordinates now. We can turn a complex number into polar form. Now, we're going to use these tools that I have highlighted here. Those are the things that we're able to use. Cosine is equal to your a value over r, sine is your b value over r, and then r is just going to be the absolute value of that complex number. So this is the general form of a complex number. Okay, this is rectangular form. So that's rectangular form. This is the polar form of a complex number. R is called the modulus, or multiple would be moduli. And then the angle theta is called the argument. Okay, so I know that's a lot of new terminology. That's just what you're going to need to be familiar with. But let's go ahead and do a couple examples here. So it says plot -2 minus 2i in the complex plane, and then write it in polar form. So we're going to plot this point. 2 on the real, -2 on the imaginary, and that's our point there. And then we want to find what this is in polar form. So our r is from the origin to that point, and we have 2 and 2, so this will be 2 squared. Let's go ahead and okay. And then we have 4 and 4, so r squared equals 8. And then r equals to √2, or the square root of 8. Okay, so we have z is equal to r cosine theta plus I sine theta. And we know what our r value is. It's 2 √2. cosine, and we need to find out what theta is. Well, we can think about this angle here, and if this is 2 and 2, that would be a 45-degree angle in quadrant 4, which is 7 pi over 4. And so that is our number in polar form. We can look at our next example here. It says write z equals 2 cosine 60 I sine 60 in rectangular form. Well, first thing we want to do, actually we don't even need to graph that. What I can do is just evaluate this. So 2 and cosine of 60 is 1/2, and sine of 60 is root 3 over 2. And multiplying by 2 everywhere, we have 1 plus I root 3. And that is in rectangular form. Okay. All right, so let's talk about multiplying and dividing in polar form. Okay, so the formula for the product of two complex numbers in polar form, we multiply the radii out front and then we add the angles inside. So if that's what we do for multiplying, then for dividing, we divide the radii and we subtract the angles inside. So let's go ahead and do an example here. So we have 12 cosine 3 pi over 4, I sine 3 pi over 4, and then our second one is 4 cosine pi over 4 and I sine pi over 4. And it says find the quotient. So we're dividing, so z1 over z2 is going to be 12 over 4. And then we have cosine of 3 pi over 4 minus pi over 4 plus I sine 3 pi over 4 minus pi over 4. And 12 divided by 4 is 3. And we have cosine 3 pi minus pi over 4 is going to be 2 pi over 4, which is pi over 2, plus I sine pi over 2. Okay, now it said to leave it in polar form, so this would be polar form. That means that's our answer. Now, so far we've done things that we have always been able to do with complex numbers. We've always been able to multiply, divide, add, subtract, and now we're able to find the absolute value of complex numbers. But the reason why we want to use polar coordinates is because it allows us to do new things. We've never been able to square complex numbers or raise them to higher powers. We've never been able to square root complex numbers, but in polar form we will be able to, and that's what de Moivre's theorem is all about. So now that we're at de Moivre's theorem, we're going to go ahead and do the things that we've never been able to do with complex numbers before. Now we can raise it to a higher power, and by doing that, r is to the higher power, and then we're multiplying by that inside. So let's go ahead and do a couple examples. It says find this complex number 2 cosine 20 I sine 20 to the 6th power and write your answer in rectangular form. Okay, so this complex number to the 6th power, we have 2 to the 6th power and then cosine of 20 degrees times 6 plus I sine 20 degrees times 6. And 2 to the 6th power is 64. Cosine, and 20 degrees times 6 is 120. But it said write our answer in rectangular form. Cosine of 120 is -1/2, and sine of 120 is root 3 over 2, and we're multiplying by 64, so that gives us negative 32 plus 32I root 3, and that's our complex number raised to the 6th power. We can do another one. It says we have 1 plus I to the 8th power. We want to do this using de Moivre's theorem. And then we want to write our answer in a plus bi form, which is rectangular form. Okay. Well, right now we have this in rectangular form. We need to figure out what is this in polar form so that we are able to raise it to that power. So we have 1 and 1. And that would be the pi over 4. And r, well, 1 plus 1 is going to be root 2 for our radius. Okay. So z is root 2 cosine of pi over 4 plus I sine pi over 4. And we're raising z to the 8th power. So root 2 to the 8th power, and then we have cosine of pi over 4 times 8 plus I sine pi over 4 times 8. And root 2 to the 8th power is 16. And pi over 4 times 8 is going to be 2 pi. And it asked us to write our answer in rectangular form. Sine of 2 pi is 0, cosine of 2 pi is 1. So there's no imaginary part. I times 0 is 0. So we have 16 times 1, and so our answer is 16. It's crazy that you can raise a complex number. We have a complex number here. Raising it to the 8th power turned into a real number, like 16. Okay. And I think I'm going to stop us here, and then we will do part 2 of the video where we start to look at the roots of complex numbers.